Sandy and Matt, I summon you.
You
Hi.
have called us.
Awesome. All
You
right.
summoned me from the depths of the Admirals Club at Phoenix.
All right. Well, hey, everybody. Welcome to the Weekly Space Hangout for Friday, June 26th. Yes, I looked down at my calendar. 2015. So this week, we're going to be talking about Philae Reconnected, the LightSail, and some missions to Europa, as well as some under ice rovers. So joining us this week, we've got Alessondra Springmann, who mentioned she's in the Admirals Club in the the Phoenix airport.
Yeah, because there's no Wi-Fi that's reliable in the airport, and there's certainly no power outlets.
Well, it's working great. So, and I think we really love your background. It looks really spacey. You have to hold on a second. I'm going to click on you there now, so you can see all of these like little LED lights up in the ceiling there. I'm super jealous. Like I said, I'm gonna build this above me. I'm gonna paint it black, put a bunch of LEDs up there. Yeah,
What you do is just make panels and stick it up there, so you don't have to paint your ceiling permanently black.
It looks like an old
that's
school
a good
planetarium.
Yeah, it does.
That's really smart. Just like build it into the into the
make
actual
a drop
substance and
ceiling.
then put that up there. Yeah, that makes sense. Okay.
And
Our special guest this week is Paul Sutter. Hey, Paul.
Hey.
So
everyone.
for people who don't know, you are what, a visiting fellow at Ohio State University and the host of Ask a Spaceman.
Yes, I have to correct you. It's the Ohio State University. For some reason, they insist on the article there, so you're not confused like some random Ohio State University in the middle of Delaware or something.
Right.
It's the one in Columbus, Ohio. Yeah, I'm a visiting scholar there, and I also I actually get paid from a fellowship based in Trieste, Italy. And so I'm back and forth between Italy and the U.S. all the time, and I'm the host. That would be me. I'm the spaceman.
I think your internet just cut off there for a second. I don't know if Sonny
Of course
saw
it
that
did.
too.
Yeah. I thought it was
Yeah.
mine. I thought I closed the tab.
Okay, it was probably my fault.
You want to take another crack at that? Whatever the thing you just said about the host? What we got was I'm the host, and then just this sort of
I'm
dead
the
air.
host. Yeah. So I'm the poorly connected host of the Ask a Spaceman podcast, where you ask questions online, or when you bump into me on the street, and I I answer them on a podcast and YouTube series.
That's fantastic. And so I actually took a look at some of the recent episodes, and I think we've got a little more time this week. So I was planning to maybe take some of your questions and sort of reshoot them at you, let you give the answer, and then I will ask even harder versions of those questions. So you
Okay,
really
let's play.
All right, let's do it. There's a very classic episode of Astronomy Cast where I was able to ask my hardest questions, and literally I have saved up 3 years of difficult questions. Or 7 years, sorry, of the questions that Pamela, it's like, we just can't do that one, too much math. So.
Oh yeah, well, there's a chalkboard right behind me.
Yeah.
So Matt,
You'll do
I'm
the
all
math.
for math.
Oh,
I'll do
awesome.
math.
Okay, great. So now, Sandy, I know you are actually in the midst of preparing for 4 talks right now, and you've got like 70 minutes.
When Pamela Gay asks you to give talks because she's double booked herself and wants to spend the weekend in a castle somewhere in the Midwest with her husband and friends, you say, "Yes, Pamela, I'll give talks for you."
Yes, we've all heeded the call. So anyway, so if Sandy looks distracted and is like working on something else, please don't hold it against her. She is literally attempting to prepare some really important talks. So yeah, and we appreciate her being able to make it to today's episode. So this is a live episode. We're doing this live. You can ask us your questions about space and astronomy and talk about the subjects that we're talking about this week. And the way you do that is wherever you're watching this, just click the video. Just madly click the video wherever you're watching. That should just bring up the Q&A app, which you'll then see the video, but also a bunch of comments and questions over on the side. And just to demonstrate that this is actually happening, I'm going to say hello to a bunch of people who are watching. Nancy Graziano and Alexander Howlett and Linda Sadiq and Don Sudeth and Guido Bibra and Jim Meeker and Tony Lynch, Tom Van Scotter, Ignatiy Romanow Cherengovsky, Andrew Planet, Rick Schwartz, Lionel Ward, Richard Clark, Ilad Avron, C. Rose, and Richard Strassel, and Thomas Traniker. So, hey, everybody, thanks so much for joining us this week. We really appreciate it. And now go ahead and delete your comments so that I can just see the questions. That would be super. Okay, great. Well, let's get on to we're gonna make this a little strange, which is that Sonia doesn't have a lot of time. So first, we're going to talk about a bunch of topics that are interesting to that she's been following, and then we'll segue into interviewing Paul, and then we're going to talk about other stories that Paul has been following as well. So it's going to be a little weird. I apologize in advance, but you know, you can handle it.
Or you know, Paul can go first, and I can just hang around, and you can come back to me. And
no. Let's
whatever
we'll
works.
have some opinions as well. So let's first just talk about Philae.
All right, let's talk about Philae. So as you may remember, in November, the Europeans landed the Philae lander on comet Churyumov-Gerasimenko. So this was Rosetta mission to this comet, and so they designed this mission expecting to land on a much more round object, and when they rolled up to Churyumov-Gerasimenko, they realized it's a rubber duck. And so Philae was expected to harpoon this comet and land in a sunny spot where it could keep communicating with Rosetta, but it bounced 4 times. It won the high jump in the Winter Olympics, and it wound up landing in a spot that is a little cold and a little dark. So since November, it's been hibernating, and finally it woke up and it talked to us. And so it's minus 35 Celsius there. It has about 24 watts of energy, and it's been communicating with its team on the ground via Rosetta. So this is the first time since November we've talked to the spacecraft, so that's over 6 months. And it turns out that Philae doesn't just woke up. It's woken up a couple of times before, but for whatever reason it wasn't able to contact Rosetta or communicate with Earth. So there's still a lot of data that needs to be downloaded from Philae to Rosetta, and so there's probably a lot more that we can learn about what's going on in the comet from having a lander there, and maybe it has some information from when it couldn't communicate with us about what it's been up to, what it's been seeing.
Yeah. I mean, I know that the way the comet works and where Philae is on it, right? The comet is turning, and so there's times when it and Rosetta sync up, and they can do this. And I know they can only communicate once every 12-ish hours, and so they've made these communications like about 6-7 times so far.
Yeah, they've been trying since March to listen for a signal from the lander. I mean, so it got 60 hours of operation, and then goodbye. So. And now it's finally found us. It called ET phoned home.
So, Paul, have you been following the Rosetta mission?
Yeah, it's really exciting. I think one of the things I really appreciate about the whole mission is just how insanely hard it is to land a probe at shooting things at comets, but not gently landing on comets. And so just the fact that it didn't disintegrate immediately upon landing, that it actually had 4 reasonable bounces and then settled down, I think, I don't know, I just like celebrating things that are amazing about human achievement. And I think landing on a comet should be up there.
So, Sonny, does this give you pause for I don't know if people know that you're working on the OSIRIS-REx mission, that that it's very dangerous to land a spacecraft on the surface of a comet or asteroid, and just not to mention attempting to retrieve something from its surface?
Well, I think the OSIRIS-REx mission is going to have it a little easier than Rosetta did rolling up to Churyumov-Gerasimenko, because we know what the shape of the asteroid is ahead of time from radar observations and radar modeling done by Mike Nolan and Carl Hergenrother. So we have an idea of how big the asteroid is, what it's shaped like, what it's made of, and a little bit more about the surface. We don't know what the cohesion is, and the other thing is we're not landing on the surface. We don't have a lander. We don't have to stick a landing. All we have to do is have a sampler hit the asteroid, collect material, and land back, come back up. So you're not sticking around on the asteroid for any amount of time. It's really just taking some rocks and going home. The Japanese, who are rolling up to an asteroid right before OSIRIS-REx gets to its, they have landers, they have bombs, they have all sorts of strange kinetic impactors. Probably not things to say in an airport. But they really have this Christmas tree spacecraft that's going to throw everything at an asteroid, and they kind of have a shape of the asteroid. They know some things about the asteroid, and we know a lot more about our asteroid targets than the Europeans knew about Churyumov-Gerasimenko when they designed the mission. Like I said earlier, Philae was designed to land on a stress ball, not a rubber duck.
Right, right.
And to answer everyone who's asking where I'm... Sorry, a couple people are asking where I'm doing the show from. It's one of the lounges at Phoenix Airport, since I have a 4-hour layover here.
Yeah, yeah. So, all right, so then where will things go sort of from this point on? Now that they've been able to communicate with Philae, you said there's like a pile of data they need to download and get off the lander. It
looks like it's woken up before, so it might have some information on temperature, magnetic fields, or lack thereof on the comet, electrical conductivity, which can tell you a lot about the material that the comet's made out of, how much rock versus how much ice, and then eventually it'll start taking photos again and start doing radio, and that would help find out where exactly the lander is on the comet, because I don't think we're entirely sure. And then also it has a drill on board. Philae is not just a sort of passive data taker. I mean, it did have the harpoons, but it's got ovens that you can heat samples in to determine composition of the comet and drill down to below the comet's surface.
I think I read that the drill isn't going to work. I'm not too sure about that.
Well, if the drill doesn't work, don't hold your breath on the drill, but at least maybe it can do some studies of the surface, because this is the first time we've really landed on a comet. This is absolutely historical.
Yeah. Okay, great. Well, let's move on to the Paul part of this today's show. And so, Sandy, you can stick around if you want. If you want to log off, that is also totally fine.
Just bother me in a couple minutes.
If you just want to mute and then just keep working, that would be fine too. All right, awesome. Okay, so Paul, welcome to the Weekly Space Hangout.
Thank you very much for having me. It's a pleasure and an honor, and I say that without sarcasm.
Yeah, well, it's good. You definitely are already up to speed, and we actually have the same microphone, so hopefully this whole interview will sound very consistent.
So that's how you know I'm legit.
Yeah, exactly.
Same microphone as Fraser Cain. Then
yeah. Although I just literally bought this microphone. So the old one is gone. The new one is here. So, all right. So then for people who you talked a brief interview, but so let's kind of break this into two pieces. So for your professional side, on the sort of the research academic side, what do you do?
I do a lot of things, and so this is a 4-hour show, so I think we got 3.5 hours of this. Yeah. All right. So one of the things I work on is I'm a member of Planck, which is the European mission to map the cosmic microwave background, the very early light from the universe. I'm a cog in the very, very large Planck machine. There's something like 400 members in that collaboration, or probably even more. And so I do a couple of small things. I help with the map making algorithms and some of the statistical analysis algorithms. So if you've seen a map of the cosmic microwave background, the process of generating that map passed through my pipeline in some stage of that actual data analysis. Another large part of my research is working with a collaboration called HERA, which stands for Hydrogen Epoch of Reionization Array. You can learn about it by going to reionization.org. This is a telescope that we're building in the Karoo Desert of South Africa. It's a collaboration amongst various American institutions, in Cambridge, a couple European institutions, and then the University of Cape Town. And this is the telescope that's designed to look at what we call the cosmic dawn. So this is the era when the first stars lit up around 10 billion years ago, plus or minus a billion. And and to observe that for the first time, because it's a completely unexplored epoch in the evolution of our universe. So I'm on, again, I'm doing statistical data analysis with them, working on like advanced Bayesian techniques for trying to squeeze real signal, real information out of really hard to get data. But the largest part of my research is focused on what are called cosmic voids. And I got a question from Richard Clark, who's a big fan of cosmic voids. So you're like one of the 10 people in the world.
Oh, this one comes from Adam Synergy.
Cosmic void is.
The name of the person was below, not above. But I'm sure Richard Clark is a huge. Yeah, Richard Clark is. I know Richard. He's a huge fan. Yeah, as well. Really, everyone who watches this show is a gigantic fan. I don't know. Yeah. Go ahead.
Of cosmic voids.
Yeah.
Okay, yeah. So cosmic voids are the largest things in the universe, second only to the universe itself. When we zoom out on the scales, we go out of the solar system, we go out of the local group, we go out of the Milky Way galaxy, we go outside of the local cluster of galaxies, and we zoom out to the very largest scales in the universe. We see that galaxies just aren't scattered around randomly. Galaxies in our universe actually form a pattern. There's a structure to the way galaxies are arranged in our universe, and we call this pattern the cosmic web because it looks like a web. So the people who first discovered it, they said this looks like a web, we'll call it the cosmic web. This means that there are there's dense clumps of galaxies of like 100 galaxies or 1,000 galaxies. We call those clusters. There's even walls and sheets of galaxies, and then what's left behind are these big empty spaces that have no galaxies in them and also no dark matter in them, and we call these the voids. And so I study the voids. I study the properties of their voids, the evolution, both in simulation and theory, and also in observations.
But that sounds
so you can actually go if you want to. Yeah.
There's nothing.
It's actually.
Right. No, I'm sure it's.
Yeah, we look where there isn't stuff. Yeah.
Yeah.
It's like the analogy. If you're looking at a spider web, you can either characterize the spider web if you're trying to perform a statistical analysis of the spider web. You can look at how long the ropes are or how many different nodes of connections there are, or you can look at the shapes of the holes, the sizes of the holes. It sounds easy, and with your eyeballs, it's pretty easy to pick out the voids in the cosmic web. But we need computers to do it because the universe is a really big place, and we can't afford armies of graduate students to do it for us. So we have to develop sophisticated computer algorithms for detecting the voids, getting their properties, and then from there, taking that collection of properties, like what's the average size of the void, what's the average shape of the void, and connecting that to things like what is the nature of dark energy, or how much dark matter is there in the universe. Trying to make those kind of connections so that we can use voids to understand more fundamental things about cosmology.
And I understand that a lot of the research is big work in simulations, and in fact, I know that researchers have really come a long way in the scale and degree and accuracy of the simulations they've been able to do, from really when you get to the reionization period until quite a few billion years into the evolution of the early universe, that you get these same structures. You get these walls and strings of galaxies, and then these voids. And I guess is it a situation where it's sort of like the rich get richer, like wherever the concentration of matter is, that draws in more matter away from the places that have less matter, and so you get these voids opening up in those spaces.
Yeah, that's the exact picture that we have, is that much farther back in time, things were much more equal, that there were maybe slightly dense clumps of matter and slightly empty regions of matter, and these were laid down by the initial conditions just after the Big Bang. And then slowly over time, it's just gravity. So one of the nice things about cosmology, studying the universe at the very largest scale, is there's only one force that matters, and that's gravity. So we just follow the gravitational evolution of these structures, and you're exactly right. The rich get richer. If you have a slightly dense bump, you'll be more likely to attract your neighbors, which makes you heavier, which gives you a larger gravitational force, which allows you to attract more and more and more. So over time, things like galaxies form, then galaxies group into what are called groups, and then the groups glue together into clusters, and the whole time matter is streaming out of the voids and getting larger over time.
So I got a couple of questions here. One comes from Leonard Lindstrom, and this is, so there isn't even gas in a void. Is there any, I mean, apart from dark energy, is there anything in there, even individual atoms in cubic meters or kilometers of space?
Yeah, so the definition of a void that we use, that we teach computers to use, is that they don't have to be strictly 100% empty. They are what we call underdense, which is just less dense than average, so less dense than the mean density of the universe. There are regions, like the deep cores of voids, that really do have nothing. There's not a single galaxy, there's not a single speck of dark matter, there's not any extra gas, neutral gas floating around. But most of a void does have tenuous amounts of gas, does have a few scattered dwarf galaxies here and there, maybe some remnants of dark matter. The most interesting thing about dark matter and voids is if you look at this cosmic web picture, with the filaments and the clusters and the voids, and if you pick out a void and you zoom in on that void, you will see a cosmic web inside that void, but more tenuous and more thin. You'll still see filaments, and you'll still see tiny little clusters, and you'll see voids embedded in the voids. And then you can take one of those little voids and zoom in, and you see another cosmic web, but at an even lower density level, even more tenuous and faint. And this kind of rescaling properties, self-similar, almost fractal-like properties, can go from very large scales all the way to relatively small scales.
Right, so it would be the equivalent of having like spider webs within spider webs. I can just imagine some little parasitic spider. It uses some larger spider's web as just the basis of making its own little web, and it lives its whole little life within just one of those segments of the void. So one other question here. Well, actually, this sort of covered the same one, which was from Dawn. Same question. Ignatiy Romanov Cherengovsky asks, so is there any chance for life appearing in the void, vast civilizations isolated from the universe? So I guess, I mean, if you can get a star out there, you can get life, but wouldn't it be sad? They wouldn't be able to see really anything else out there, right?
Yeah, you can imagine if our Milky Way galaxy were embedded inside a void, our night sky would look pretty much the same, because our night sky is dominated by the local neighborhood of stars in our own galaxy. So you wouldn't actually tell until you did very sophisticated observations that you actually lived in a void. It's certainly possible for the few galaxies that do inhabit voids to have life in them, but it seems unlikely, or there's a less chance of life appearing in a galaxy inside of a void, because the galaxies that do appear in voids, they don't have a very high star formation rates. They're not evolved very much, which means there isn't a lot of processing of gas going on. There aren't multiple generations of stars where you can build up elements like carbon and oxygen and zinc and magnesium and all the kind of stuff you need for life. So the galaxies that we do see in voids tend to be very poor in metals, poor in higher elements, and there could be life, but the chances appear slim for inside the voids. It's suspected that we actually, our own Milky Way galaxy, is the very edge of a void. that we are in a dense, rich group, but in one direction, then you look out the other direction, and there's a very vast void on one side of our local cluster.
Right, and so maybe that would explain the great attractor, that we're on the on the one side of the great attractor. So just one thing, the technical issue, I'm getting a lot of kind of delays from you, and it feels like there's something slowing down on your computer. So have you got any kind of runaway processes going on your computer? One that's really awful is Google Drive or Dropbox. So if you're running Google Drive or Dropbox, turn those off because they will gobble up your bandwidth.
Okay.
Yeah, if you happen to have
All
them.
right, I'm shutting
Sorry,
off
it's probably the crummy
Dropbox
Admiral's
right
Club
now.
Wi-Fi. I've paused.
No,
Dropbox
you're
and all
fine.
that, but
You're fine, Sandy. It's actually Paul's. But if I've done this enough times that I can just feel in my bones that Google Drive is gobbling up your bandwidth or something. So if
I don't have Google
anything
Drive,
else,
but I do have Dropbox.
yeah. So just make sure that's turned off, and then any other processes that you're running on your computer, it feels. What kind of computer are you using? Is it?
I have a relatively old MacBook Air.
Okay, all right. There's your problem. Okay, great. So let's move on then. So that is your professional side of your job. So let's kind of move to the other side.
Yes, I study nothing.
You study nothing, yeah. Well, so great. And so with all of this free time that you have, your hobby is that you answer people's space questions. So let's talk about that whole side of your life as well.
Yeah, so about 6 months ago, I started a podcast really just for fun because people would see me working, people would sit next to me on airplane rides, and they'd start asking questions, or I'd go to a museum or a classroom, and I'd give a little talk, and then as you've experienced yourself, there's just so much enthusiasm for space. Like, people are really, really hungry for knowledge. They see Cosmos with either the older one with Sagan or the new one with Neil deGrasse Tyson, and they get a little taste of something, and if they get interested in it, you just want to dig in. You want to learn more. You get excited by it. So to kind of help that, to answer people's questions, I started a podcast called Ask a Spaceman, where I'm the spaceman. And people submit questions online, either Twitter or Facebook, using the hashtag #AskASpaceman. You can also email askaspaceman@gmail.com. You can call me up if you actually know my phone number. We just ask questions, and I put them on a list, and then I group questions together, and I answer them. I have 2 episodes per month. Each one is between like a half hour and an hour, just depending on what kind of questions and how much detail I need to sink down into the topic. And it's just been a blast. I've had a lot of feedback, tons of great questions, more questions than I know what to do with, so I'm trying to figure out how to answer them on a faster production cycle while balancing it with my day job.
Yeah, welcome to the club.
But it's just so much.
Yeah. Okay, so I thought I would do is, you've got a couple of questions recently, and I thought I would give you a chance to answer them again, but this time live. So let's just go with because I think this sort of fits with your research, which is, how big is the universe?
The universe is really honking big. And like it's one of these things that you can attach numbers to. Like, oh, the universe is 90 billion light years across, or something like that. But that just has no meaning to anybody. It doesn't even have meaning to me. I think a lot of cosmologists, we're so used to running computer simulations, we're so used to doing galaxy surveys, and we rescale everything to have nice, neat little numbers, but we just treat like the entire universe as just some abstract object. And if you actually sit back and take a breath and think about, say, what are the real dimensions of this particular cosmic void that I'm studying, and it's like, 20 million light years across, at a minimum for a cosmic void. And it's just mind-bogglingly vast distances. So the universe is big. But that's the observable universe, which is how far we can see given our light cone. So the universe has a certain age. Light moves at a certain speed, and so you multiply those together. You have to fudge a little bit because the universe is actually expanding with time. So when you crunch the numbers, it's like 90 billion light years across, something like that. But the full universe, which is what essentially more stuff that we'll never be able to see because there isn't enough time for the light to beat the expansion of the universe. So if there's a galaxy way out far away, that light will just never reach it. Us in time, we'll never see it. It's more of the same, so there's just more of this cosmic web pattern, but just kind of repeated, with modifications all over. That's just huge. If you thought 90 billion light years across was huge, the entire universe is like 10 to the 60 things. And it doesn't matter if you're talking meters or light years, 10 to the 60 of whatever is a lot. And it's just incomprehensibly big. Yeah.
Right? I mean, you say that it is 10 to 60. I mean, I know, like, we talk about, say, the observable universe, we're looking back in time 13.8 billion light years in all directions, but as you said, even though the light you're seeing, the objects you're seeing 13.8 billion light years away, that stuff has moved out to 93 billion light years across, but then outside that is stuff that we will never see. We'll see some stuff, I guess, every year that goes by we'll see another light year out, but really, but then because of the expansion of the universe, some of that stuff is eventually moving away from us at faster than the speed of light.
Yeah, actually, I think we see less and less every year because because of dark energy, the expansion of the universe is accelerating, which is beating the speed of light, so it's actually carrying galaxies away from our light cone, which just sucks.
Yeah, totally. So, but this is a tiny little fraction of the actual universe. So here's here's where I make your question harder. Is it finite or is it infinite?
So we don't know. Actually, it could be infinite. The universe just could be infinitely big, or it could be finite. There's no real reason to pick one or the other, finite or infinite. It doesn't affect us. It doesn't affect our observable patch, our little bubble that we can see. And whether it's infinite or it's 10 to the 60 light years, it's still huge. And so it doesn't matter. That's my answer.
But how could you have... but yet the whole universe was enclosed within the singularity at the beginning. So how could you have an infinite universe which was enclosed within a, infinitely dense little area?
Yeah, so we have to be careful when we push back to the Big Bang. So the Big Bang is not a theory of the creation of the universe. It's a theory of the evolution of the universe moments after the Big Bang. When you get closer and closer to that singularity, when the universe gets smaller and smaller and hotter, the physics become harder and harder to do. Forces can merge together at certain scales. Fields and particles that don't exist today can exist in the very early universe. It's similar to conditions inside of a particle accelerator, for example. And there's a certain point where the universe is too small and it's too hot for us to really understand observationally and especially theoretically. Like, we just don't have the math to do it. We don't have the techniques or the knowledge. And so what really happens at scales below like 10 to the minus 40 seconds or so after the Big Bang, we just don't know. And we know the answer lies in some marriage of quantum mechanics and general relativity. And until we crack that problem, we can't actually say for sure what's going on at the quote-unquote beginning of the universe.
Okay, great. So let's go on to the next one here, which is that one of the questions was, how do black holes form? So how do black holes form?
Yeah, so by squeezing. I could turn you into a black hole if I tried hard enough. I could turn myself into a black hole. I forget the exact numbers. I think if you squeeze a human down to the size of the nucleus of an atom, that will that means the escape velocity off of that object will exceed the speed of light, which is the definition of a black hole. So the only thing in the universe, the only kind of large-scale force that's able to squeeze things down to arbitrarily small distances is gravity. So gravity does the job of sucking and pulling and squeezing. And really, it's just a question of what's stopping gravity from turning everything into a black hole. So if it were only gravity, everything would be a black hole already, because gravity would just keep pulling stuff in below the limit at which a black hole would be formed. So things like the fact that the Earth is made of rock, and you can only squeeze rocks together so tightly, that prevents the Earth from turning into a black hole. The sun, we have nuclear fusion, which is applying a pressure that prevents the collapse of the sun into a black hole. But eventually, things like the sun will run out of fuel, they'll run out of gas, and gravity will win, and even then, the sun will contract into what's called a white dwarf, but the white dwarf is supported by an additional pressure called electron degeneracy pressure. Basically, you can only squeeze so many electrons into a ball before they'll fight back. But with massive stars, incredibly massive stars, you can have enough stuff squeezing in from the outside where the gravity of that big ball overwhelms even that and just pulls stuff into a tight enough region to create a black hole.
Fantastic. And then, of course, we get the supermassive black holes at the hearts of galaxies. So here's your harder question. Where did they come from?
Yeah, so we think that the supermassive black holes, and super here means like at least 1 million times and usually 1 billion times more massive than the sun. We think these started out as normal, everyday, neighborhood backyard black holes, just a few solar masses. And they form in the center of a galaxy when a galaxy is very, very young, and they just eat. And they eat and eat and eat, and over billions of years, gas finds its way into the center of a galaxy and passes through the event horizon of the black hole, and that makes a bigger black hole. So it's thought that they start from normal everyday seeds, but they're just really, really hungry, and so they grow over the course of billions of years. And it's thought that every galaxy has a supermassive black hole at its center.
So let's move on to the back to the news portion of this episode, and there's a couple of big stories that I know you've been following this week. So let's start with an update on the LightSail, which, for people who aren't aware of this, the Planetary Society, of course, launched their LightSail prototype, and they just hit their Kickstarter goal, their stretch goal of like $1.2 million as part of this. So what is an update on LightSail?
So the current LightSail that was launched a few weeks ago, I believe it's already dead. They launched it into a very low orbit because that's cheaper, and they just wanted to test things out to make sure they could communicate with it, to make sure it could deploy, do its thing. They had a few hiccups, which is, I mean, this was a test run that they did, and so they had to test a bunch of things. And I think it's already burned up in the atmosphere, and if it hasn't, then it will any day now. So what I think this Kickstarter is for the next generation of LightSail, and I think they reached their goal where they'll be able to get it, they'll be able to afford to have it launched into a high enough orbit where they can actually deploy the sail and actually try to cruise around using light, or at least test to make sure they can get some actual impulse from the sails.
Yeah, and so I know with the LightSail, this is the LightSail A project, and the LightSail 1 is that they're going to actually take this thing and launch it into next year, I think, and put it into a further orbit and really see if you can get that propulsion from the light of the sun. Which
they're not at the stage yet where they're actually like doing interplanetary cruises yet,
or interstellar cruises. Yeah.
Yes.
Yeah. I mean, light sails are really fascinating to me because I always sort of imagine that it would be a great alternative sort of backup transportation system that you could put onto almost any spacecraft. Like once they come up with some system that works really well, they could just add almost like a lifeboat, just bolt it onto the side of your spaceship, and for example, if your gyros, you run out of gyros and you need to still turn your spacecraft, you could deploy the sail and use that for reorientation. Or if you need to, kick a little more, a bit of a modification to your orbit, then you've got a way to do it. So it's pretty exciting. I'm really glad that the Planetary Society has sort of pushed this project so far.
Yeah, I could really see light sails being really useful if we ever get a colony on Mars, and we need any Mars colony would be totally dependent on Earth for quite a long time with a regular chain of supplies. And so each individual craft to Mars, if it was equipped with a light sail, would take a very long time, but you could send up like a convoy. So like every 6 months there's a return craft, and the sun is providing all the propulsion you need, so it's a cheap way to kind of shuttle supplies between the Earth and Mars.
Yeah, no, it's terrific. So I guess the next big thing for us to watch is the LightSail A project, which is going to be happening. But if you haven't already, I mean, you can go ahead and put in some money into the LightSail project. Just do a search for LightSail Kickstarter, and you can join that. I know Bill Nye and the rest of the Planetary Society team will be much appreciated for any donations you can kick their way. Let's talk about missions to Europa.
Yeah, so as long as you don't land there, you're good.
Isn't that's the one that we've been informed is a world that we're not to attempt any landing on?
Yeah, attempt no landings there. But here we are, doing our best to try land something there. I think so. NASA just announced a couple weeks ago that they've entered into a development phase, which for NASA development means you get like tens of millions of dollars instead of hundreds of millions of dollars. They've selected a mission to go to Europa. They've selected a set of instrument packages that will be on the mission, and the goal here is to just study Europa in more detail. So we have Hubble Space Telescope images of Europa. There was the Galileo probe that passed by Europa a few times 10 or 20 years ago, and this will be one that's especially designed for Europa to really get a handle on how thick is the ice, what is the content of the ocean, how salty it is, are there other minerals floating around, how common are ice plumes on the surface, how tectonically active is the ice surface, and also is there possibility of life? Can we detect any, say, amino acids or basic molecules necessary for life? Do those leak out? This mission is useful scientifically just as a mission, but also as a preparatory step for if we wanted to attempt drilling down through the ice of Europa. We really need a better handle on. We need a better picture. We can't just go send. Was it Bruce Willis? Where we sent the oil rig. We can't just send a crew right away, and then it turns out there's 100 kilometers of rock hard ice. We need to study it more. And so that mission where we actually try to drill down into the oceans is pretty far off in the future, and this is like the logical next step to get us there.
Yeah, and that's like the most exciting scientific package on the potential mission is the radar array that will allow it to penetrate the ice down and try to figure out what it looks like underneath the ice of on Europa. Are there pockets of water? Is it and is that subsurface ocean 10 kilometers down, 100 kilometers down? Like there's a certain limit, and I know that the power draw on this mission just from this radar package is going to be tremendous, and so this is something that a lot of people weren't big fans of, but I think the sort of enthusiastic hope for the unknown has ensured that this mission will still, or this scientific package will stay on the mission, even though it's going to be it's going to guzzle a lot of power. And I know Sondi, as a radar operator with the Arecibo Observatory would appreciate the fact that a pretty powerful radar system is going to be going directly to Europa. So if everything goes well, when will this thing head off to Europa?
I think it's scheduled for the 2020s, which, knowing NASA, that's going to be like 2040, 2050, sometime before the 22nd century, for sure. But it's slated for the mid-2020s to launch, and then it will take a few years to cruise out to the Jupiter system, of course.
Yeah, and the typical way that these missions go, right, is you do flyby, orbiter, lander, sample return is the chain of missions. So we're now, I guess, reaching, hopefully we'll hit level 2 on this and maybe get an orbiter if we're lucky. So I've got a couple more questions here from people. This comes from Alexander Howlett for you, which is, speaking of particle accelerators, do you expect the Large Hadron Collider to offer new insight into these extreme regions of the universe? So, a lot of your work is in dark matter, dark energy. Do you think that the LHC is going to help you figure out what dark matter is?
Yeah, absolutely. So you run these big particle colliders and you make a bunch of exotic particles that don't live long under exotic conditions with exotic interactions. There are some candidates for what dark matter could be that might be accessible with an instrument like the LHC. You won't see the dark matter particle itself because it's dark, but you would see it's like leftovers. You'd have a particle missing in your shower from the collision. So yeah, the LHC could be a dark matter factory for certain kinds of models, and if it doesn't discover it, well, then that rules out that class of models, and we learn more about the nature of dark matter. Also, the mission of LHC is to explore fundamental physics. And while it can't reach the energies and densities and temperatures of the very, very early universe, the more we know about the puzzle of fundamental physics and how forces join together at high energies, the more we learn about the early universe and the processes going on in the early universe, and the more we know about the Big Bang. So it's linked. These small scales studied with high energy particle colliders are intimately connected to the large scale physics that we study in cosmology.
Awesome. And I mean, they've just, doubled the power of the LHC. They just got that running within the last month or so. So
Yep.
Hopefully, we're going to get a whole pile of new information this time around.
Yep, this year.
Okay, so here's a great one. This comes from Lionel Ward, and this is, what happens when you travel to the edge of the universe?
Well, the universe, you have to be careful of what you mean by edge. So edge could be the edge of the visible universe, so the little bubble that we can see. You'll never get there because it's expanding faster than the speed of light. So you'll never get there, so moot question. And then if there's the larger question is, if the universe is finite, like we talked about before, even this full 10 to the 60 gigantic universe, even outside of our tiny little bubble, if that has an edge, could you travel to that edge? That's like asking if you lived on the surface of a ball, like we live on the surface of the Earth, asking where is the edge of the Earth? Even though the Earth is finite, the surface of the Earth is finite, there is no edge. And
right.
So
you could travel
yeah.
in any one direction. If you're an ant crawling on the surface of the Earth, you could travel in any one direction, forever, on a ball, right? You could travel on a ball for it, just around and around and around. And if you inflated the ball and it would be twice as big, you would travel twice as long, but you would still return to your starting point.
Yep.
But then this is the part that kind of breaks people's brains, is they're like, well, yeah, but I can see the ball, and I could see that the ball is just this ball in the middle of a larger three-dimensional space, and the ant that's trying to crawl on it is just an idiot.
So it could jump.
So it could jump, yeah, it could jump. And yet when we imagine the universe, we imagine this ball, this expanding ball. Where do our
What is the universe?
Are we the ant? Are we the idiot? Yeah. Could we jump?
We are the idiots.
Yeah.
But yeah, and this is kind of like a fault of the poor analogy. Like the idea of ants crawling around on a ball is like the best analogy anyone has. But we did a cheat. We did a cheat because we imagined the ants crawling around on the surface of a two-dimensional ball. But to think of it, we all know that balls are three-dimensional. We live in a three-dimensional world. So we can like sit outside of the ball and consider it and think about it and watch this ant just crawling around without realizing it can tunnel through or it can jump out. So it could be that our three-dimensional universe, three spatial dimensions, are embedded in a higher dimensional structure, and that this is what's happening, is our three-dimensional universe is expanding into a fourth dimension. Just like a two-dimensional ball, it can expand in a third dimension. That could be the case, but it doesn't have to be. The universe, we can describe the evolution, the expansion, everything about the universe using just three dimensions, and all the math just works out fine, and we're using math to describe the universe, and it works. We don't need extra dimensions. There could be, but there don't have to be. And like, it breaks your brain, and it breaks my brain, but the math tells me that it works, and we don't need it. The universe can expand without having anything to expand into.
Right, and that if the universe is infinite and I travel in one direction, I could just travel forever, and that's not a problem. And right. If the universe is finite and I travel in one direction, I could return to my starting point, like the ant?
Yes. But it'll take a while, so you better pack a sandwich.
Yeah, well, those four-dimensional aliens are just laughing at us right now as we attempt to kind of wrap our heads around this dilemma. Well, we're just kind of closing up on the end of the hour, so I think we should probably start to wrap things up. So first, I just want to thank once again the WSH crew, the Weekly Space Hangout crew, which is the Google Plus community that has helped to organize Paul's attendance on the show today. And Paul, you're a member of the crew, and you're also, it's very meta.
Yes, I organize myself.
Well, that's great. Any other working researchers and or space podcasters who want to join the show and are also part of the crew, go ahead and nominate yourself. We'd love to have you. So where can people find out more about what you do?
Oh, man. You can find me on Twitter at Paul Matt Sutter. Also on Facebook, Paul Matt Sutter. That's my name. You can go to askaspaceman.com. You can also search on YouTube. I have a new series with Wayne Schlingman, who is the Ohio State University Planetarium Director. We have a show called Space in Your Face, where it's the latest astronomy news in 2 minutes or else. It's just a fun, dumb show where we just goof off for 2 minutes, and we pretend this is space news. But you can search on YouTube, Space in Your Face. You can also go to pmsutter.com. That has links to like all my shows and all my appearances, everything I do is pmsutter.com.
That's terrific. Okay. Sondi, where can people find out more?
I'm on Twitter as Sondi. I should be blogging for other people, but I haven't been, so sorry. I'm a nuisance on Twitter. You should follow me.
I will second that. Awesome.
I don't know if to take that as a compliment or not.
And if they want to, you said it, if they want to follow your professional work, though, as well as the missions that you're involved with, where should they look?
Follow Osiris Rex, OSIRISREX on Twitter. It's Osiris_Rex on Instagram. I think the mission is also on Facebook. They're doing pretty well on social media. So definitely check it out. They just got delivery of their first instrument, which is a thermal imager from our friends at Arizona State University, which is pretty cool. So
that's awesome. Yeah. I mean, right now we're all thinking about Rosetta, and we're thinking about New Horizons, but years from now, this is going to be the mission that we're all going to be just freaking out about and so excited about, is the fact that we are landing on an asteroid and retrieving a chunk of it and bringing it back home
And this is, we're going to get more than they got from, what was the last, Hayabusa going to Itokawa. They only got a little bit of sample, and so we're going to be going to a very primitive asteroid that we think hasn't changed much since the origin of the universe. But I got to run because my flight takes off in 40 minutes. So.
Well, we've all got to run.
You got a jet.
So
I've literally got a jet.
You've got a jet. All right. Well, thanks, Sandy, and thanks, Paul, for joining us this week. As always, you can follow me.
Some other time we'll talk about under ice rovers.
That would be great. Yep. And you can reach me on Twitter at @fcain. And one last little announcement, which is I don't know if we're going to do another weekly space hangout, but I know a week from now we're going to do the 4th episode of our hangout with New Horizons folks. So that's coming up in about a week
They're really
from now.
great. I love them.
Yeah.
They're so. Oh my God, New Horizons. We're rolling up to Pluto. We've never been to Pluto. This is the first mission to the last planet. It'll probably be the only mission to the last planet. So,
yeah, we're only just over 2 weeks, 2.5 weeks until we get these first close-up images of Pluto, and I think this is going to be one of the most exciting things in space astronomy in the decade. So,
there are a lot of Pluto people and press people moving to DC for the next month to cover this. It's going to be groundbreaking. It's going to be earth-shattering. It's going to be world-changing.
Yeah, absolutely. Maybe, hopefully, planet reacquiring. If that's a red herring, man. That is a red frickin' herring. I have shrimp. I don't have a red herring, but like. Yeah. No, and I know the IAU is going to be meeting in Honolulu next month, and that is not something they're going to be voting on.
Good.
They're not going to be voting on whether or not Pluto is a planet again. All right. Well, I know you guys both have to run. I got to run, so I'll wrap this up. Thanks everyone for joining us this week.
Thank you very much.
For possibly the ultimate. Maybe the penultimate. I'm not really sure. Again, I'm
quasi-ultimate.
The quasi-ultimate episode before we do our summer hiatus, and then back after Labor Day. So, thanks for the guests. Thanks for everyone watching, and we'll see you all at some point in the future. If you like the backdrop here, read stuff. Buy me things off my Amazon wish list. I don't know. Shameless self-promotion. Right. I had to get Wi-Fi to do this. So. All right. Thanks, everybody.
Thank you.
Bye.